Let us start compiler design unit 5 code generation. So in this topic we will discuss about in this unit we will discuss about code generation and code optimization. So code generation is the last stage of compiler design, and here we will talk about first design issue. So in case of code generation, it is a final phase and it takes intermediate representation as a input and provides the corresponding target program. You can see here in diagram. So we have your front end source program as a input, intermediate code as a input. In middle there is also a code optimizer. We will talk about that code optimizer also, and intermediate code is given as input of the code generator and provide the target program. The code generator has three primary tasks. So first task is instruction selection, which instruction is to be used. Second task is register allocation and assignment. Third task is instruction ordering, in which order instructions should be there. So in case of instruction selection, it involves appropriate target machine to implement the instruction registered statement. And register allocation and assignment, it involves deciding what values to be kept in in which register. And instruction ordering involves deciding in what order the schedule execution of the instruction, so in which order it must be executed, which this is to be decided here. So what are the issues in design of code generator? First, the issue is input of code generator. The input to the code generator is IR, that is intermediate representation of the source program, which is produced by the front end, along with the information of symbol table, which is used to determine the runtime address of the data object denoted by IR. Many choices of IR includes the following. So intermediate representation can be in quadruple, it can be in triple. In virtual machine, it can be in the form of white code or stacked machine code. Linear representation can be there with postfix notation, and graphically it can be in syntax tree and the DAG. That is so okay. So second is the target program. So second issue. So in target program, the instruction set architecture is to be decided of the target machine to produce the high quality machine code. And the common target machine code architectures are RISC, reduced instruction set computer, CISC, compressed instruction set computer, and stack based machine. A RISC machine typically has many registers, three address instructions, simple address modes, relatively simple registration set of architecture. But in case of CISC, it may have very few register, two address instructions, a variety of address modes, several register classes, variable length instructions is allowed here, instructions with side effects here we have. A stack based machine operation are done by pushing the operands onto the stack and performing the operation on the operands at the top of the stack. To achieve the high level performance, top of the stack is typically kept in register. A stack based machine is almost disappeared because it was felt that the stack organization was too limiting and required too many swap and copy operation. However, the stack based architecture were revived with the introduction of Java Virtual Machine (JVM). That is, JVM is a software interpreter of the Java bytes and intermediate language, which is produced by the Java compiler. The interpreter provides software compatibility across the multiple platform, a major factor, which is the major factor in the success of Java. The third issue was instruction selection. The code generator must have the intermediate program in to a code sequence that can be executed by a target machine. The complexity of performing this mapping is determined by the different factors such as level of intermediate representation, nature of instruction set architecture, quality of generated code. Intermediate representation of the high level, the code generator may translate each instruction intermediate register statement representation statement into sequence of machine instruction using the code templates. Such statement by statement code generation may produce not a good code, and it may further need some optimization. Intermediate code representation reflects some of the low level details of the underlying machine. Then the code generator can use this information to generate more efficient code sequences. Instruction speeds and machine items are important factors. If do not if we do not care about efficiency of the program, target program, instruction selection of straightforward. Each type of three address statement can be designed a code skeleton that defines the target machine to be generated for the construct. For an example, in three address statement of the form x equal to y plus j, where x, y, z are statically allocated, can be translated like this: load r0 comma y, that is r0 equal to y, add r0 comma r0 comma z, that indicates that we are just adding y plus z here, and st stands for store x comma r0, so value of r0 is stored in the x. This strategy often produce redundant load and stores. So number of load and store is redundant. So what we can do, we can use like this: for a equal to b plus c, d equal to a plus e. If the template is used, we should use like this: load r0 comma b r0, add r0 comma r0 comma c, a comma r0. And for d equal to a plus c, we should write like this: load r0 comma a, add r0 comma r0 comma e, d comma r0. So if we are using the template, so here the fourth statement is redundant: 1 2 3 and 4. So this is the fourth statement, this is redundant statement, since it loads a value that has been stored. So the third, so as in the third, so third what we are doing, we are just storing the value of r0 in a, so we do not need to load again the value of a into r0. So what we can do, we may remove the fourth statement from here. So this is known as the optimization. So the quality of generator code is usually determined by its speed and size. So we need to optimize these codes. For an example, if we want to have a inc, that is the increment, that is the a equal to a plus 1, then we need to write like this: ld load r0 comma a, r0 equal to r0 plus 1, and store a comma r0. So here is one of the example for the increment part. In case of register, the key problem of code generation is to decide what values to be held in what register. So register are fastest computational unit of the target machine, but it is usually not enough to hold all the values. So we need to store these values. We use registers intelligently. Instruction involving the register operands invariably shorter and faster than those involving operanding in the memory. So efficient utilization of a register is particularly very important. The use of registers is subdivided into two subproblems. First, register allocation, during which we select set of variable that will reside in register at each point of the program. Second is register assignment, to pick the specific register that the variable will reside inside it. Example of register allocation. So we use the register pair, we set a pair. So for integer multiplication and for division, we involve the set pair. Multiplication instruction is in the form of mx comma y. So x is multiplicand, and even the register of the even odd register pair, and y is multiplier in the odd register. So product occupies even odd register pair. So if we do this, m x comma y, x into y will be happens, and result will be stored in xy. Similarly, to divide d x comma y, the even odd register pair whose value register is in x and divisor is in y. After the division, even register holds the remainder and odd register holds the quotient. So this holds the remainder and it holds the quotient. Now consider three address code sequence as shown in this figure, and this is the corresponding optimal machine code sequence. It's very simple to understand. Load r1 comma a, then add r1 comma b, m, that is multiply, d for, so first character is used here for representing the instructions. So here ri stands for register I. So this is r1 r2 r1 r0 r0, so which is in single bit. L, st and a stands for load, store and add respectively. Evaluation order. The order in which the computation are performed can affect the efficiency of the target of the program. So the evaluation order is also very important here.